Julia Olivieri, and today I'll be talking to you about examples of graph theory in the real world. This is the third workshop in a three-part series. In the first workshop, we went over basic graph definitions and terminology, and in the second workshop, we discussed several graph algorithms. If you're interested, those workshops are available on the Wiz YouTube channel, but you should be able to follow along with today's workshop without having seen the previous ones. In today's workshop, we'll start by reviewing what a graph is and why we're interested in studying them. We'll talk about data structures for storing graphs, and then we'll look at examples of real graphs and learn how to characterize them. If you have any questions today, you can post them in the Zoom chat and I'll respond. And if you're watching this workshop at a later date, then feel free to email me with any questions you have. And also, if you're interested in following along with the quote coding portion of today's workshop, you can clone this GitHub repo now. The link should be posted in the chat as well. Now let's step back for a second and remember exactly what a graph is. At its most basic, the graph is a way to represent relationships between things. So graphs are useful when we have a set of things, which can be anything from people to places to ideas, and then we have relationships that we want to encode between those things. So for example, a business organization chart is a graph where each employee is linked to their manager, and a chemical structure can be thought of as a graph where each atom is linked to all the other atoms it's bonded to. Graphs come up in many different machine learning datasets and algorithms. So for example, a neural network can be thought of as a graph where each node is connected to various nodes in the previous layer and in the next layer. Figuring out which users of a social networking site are influencers based on a social network is also a graph problem. Even studying infections from COVID-19 and how they spread can be thought of and formulated as a graph problem. So for all these reasons and many more, it's important to be able to recognize when a question can be formulated as a graph problem and to know the first steps to analyze graph data when we get our hands on it. Okay, now let's get started with some more specific definitions. You may remember from one of the last two workshops that a graph G is defined by two subsets, which we often call V and E. V is the set of vertices, which you can think of as the set of things or objects that we want to represent in our graphs. And the set E, or set of edges, is the set of relationships between those objects. So for a pair of sets V and E to represent a graph, they need to obey two specifications. The first is that V must be finite and non-empty, and the second is that each element of E must be a two-element subset of V. So, for example, these two sets totally define a graph. We can see that the set V contains a finite set of objects, and the set E contains pairs of the elements of V. Now, even though this is enough information to completely define a graph, we often find it useful to make drawings to represent graphs that can be easier to process and understand. So this is an example of how we might visualize the graph example to the left. We represent elements of the set V usually as circles, and we call these vertices or nodes. And then we represent elements of the set E as lines between those circles, and we call them edges. Vertices that are connected by an edge are called neighbors. So A is a neighbor of B, and C and D are also neighbors of B. And we let the degree equal the number of neighbors a given vertex has. So you can just count the number of edges coming out of a vertex to get the degree. So for example, B has degree 3, A has degree 1, and E has degree 0. So you can see in this drawing that we have circles for vertices 1 through 5. And then if we go through each edge in our set E, we can see that there is a line between the two circles if edge is present in our set E. So for example, there's a line between 1 and 2 to represent the edge in our set E. Okay, as we move on and start talking about using graphs in our own applications, we need to talk a bit about how graphs are actually stored in the computer. So we're going to talk about three of the most common ways to store graphs right now and talk about some of their pros and cons. First, let's talk about adjacency lists or adjacency dictionaries. So this is the storage structure that we discussed last time when we were going over graph traversal algorithms. And basically the definition of the data structure is that for each vertex, we store a list of all of the neighbors of that vertex. So if we think back to our same example graph from before, the adjacency dictionary for this graph would, for each vertex, have a list of all the neighbors of that vertex. And if all of our vertices are numbered, we can save on space by not creating a dictionary, but instead just creating a list of lists in the order of the vertices of our graph with all of the neighbors of each vertex. So you can see how this data structure includes all the information we need to recapitulate our graph. We, based on the length of the data structure, know the number of vertices in the graph. And then for each vertex, we have all the vertices it's adjacent to, so we can reconstruct all the edges of the graph. So you can imagine how the V and E sets could be recapitulated from an adjacency list. So this data structure is pretty lightweight. It only requires an order of the number of vertices plus the number of edges space. That's because we only have one list for each vertex, and for each edge, it's represented by just one element in one of those lists, or in two of those lists specifically, because the edge is marked at both the vertices of both ends of the edge. So this data structure doesn't take up much space, and it's good for traversal algorithms or any algorithms such as breadth first search, where you're interested in finding all of the neighbors of a given vertex at once, because all the neighbors are very easily accessible here. Another common data structure for storing graphs is called an adjacency matrix. An adjacency matrix is a square matrix with the number of rows and the number of columns both equal to the number of vertices in the graph. And an entry in the matrix is 1 if the vertices I and j are neighbors. So if there's an edge between I and j in our set E defining the graph, and 0 otherwise. So if we think back to our same example graph, the adjacency matrix would be just like this, where we have a square matrix with a row and column for each of the vertices in the graph, and then there's a 1 whenever there's an edge between a pair of vertices. So there's an edge between 1 and 2, so the entry 1, 2 has a value of 1, and the entry 2, 1 has a value of 1. And then you can also see that vertex 5 doesn't have any neighbors, so there are zeros in all down row 5 and column 5. The space complexity of storing an adjacency matrix is on the order of the number of vertices squared. But if the matrix is sparse, which they often are, different computational techniques can make the storage much more space efficient. And so it can actually almost rival and sometimes be more space efficient than an adjacency list if the graph has a very sparse structure. And that's because in the adjacency matrix, we only need to store single bytes to record an edge between two vertices, because an edge's presence is marked by just a 1 and absence is marked by a 0. And adjacency matrices can be specifically appropriate when we're interested in finding if an edge exists between two given vertices, because that operation can happen in constant time. We just need to look up the entry of the table corresponding to the two vertices, and if it's a 1, then an edge is present. Whereas for an adjacency list, we would need to iterate over all of the vertices adjacent to a given vertex in order to see if a specific edge existed. Okay, the third data structure we'll talk about today is another matrix representation of a graph, and it's called an incidence matrix. So an incidence matrix B is a matrix of size number of vertices by number of edges. An incidence matrix has one row for each vertex of the graph and one column for each edge of the graph. So in the column corresponding to a specific edge, if the edge is ij, then in row I of that column, if I is less than j, there would be a -1, and in row j, there would be a 1, and all the other entries in that column would be 0. So let's look at an example. For our example graph we've been working with so far, we can label the edges, edge 1 through edge 4, and then this is our resulting incidence matrix. So each column corresponds to one edge. So we can see for edge 1, we have the first column, and basically there'll be two vertices that compose that edge. In this case, it's vertices 1 and 2. So in that column of the incidence matrix, there will be a -1 corresponding to 1, which is the smaller vertex that makes up the edge, and a 1 in the second row, because 2 is the larger vertex that makes up the edge. So for each column, we have both a 1 and a -1, which mark out the two vertices that define the edge for that column. So you can see that incidence matrices have size, number of vertices times number of edges. So incidence matrices can be useful because they're not specific only to graphs. So different procedures that have been developed for more general problems, if they share an incidence matrix structure, can be still applied to graphs. Okay, now that we've talked about three different data structures for graphs, let's compare them based on their time and space complexities. So for an adjacency list, of which, as we talked about before, the storage is just on the order of the number of vertices plus the number of edges. And if we want to add a vertex or add an edge, we can do that in just constant time. We just need to add another element to the end of our list to add another vertex. To add an edge, we just need to add another element to the end of our neighbor list for the vertices that connect the edge. We can remove a vertex in about order the number of edges time, and remove an edge in about order of the number of vertices of time. And if we want to check whether two vertices I and j are adjacent, that takes time on the order of the number of vertices. So in comparison, for an adjacency matrix, we can see that adding a vertex is much more computationally expensive. It takes on the order of the number of vertices squared to add a new vertex, because we need to essentially copy the matrix and create a whole new matrix that has size n+1 by n+1. But adding an edge can also be done in constant time, and removing an edge can actually occur in constant time, which is faster than in an adjacency list. And if we wanted to determine whether there's an edge between two vertices, that is also much quicker in an adjacency matrix than an adjacency list. And finally, for an incidence matrix, almost all of these operations take order of the number of vertices times the number of edges time. And that's because we need to recreate the matrix whenever we add or subtract either a vertex or add or subtract an edge. And that's because the dimensions are based on both the number of vertices and the number of edges. So we can see that based on the specific application and which operations you plan on doing more often, either an adjacency list or an adjacency matrix might make more sense to store your graph. So you may wonder, based on this table, why we would ever want to use an incidence matrix. Well, incidence matrices are more general, and they can be used for applications other than just storing graphs. So they can be used to represent relationships between any pair of classes. So in our examples, we've looked at the two classes being the class of vertices and the class of edges, but it can be a lot more general than that. And because of that, incidence matrices are useful to know for a variety of other applications that go beyond just graph theory. So matrix structures for storing graphs have some interesting properties beyond just the simple data structure that we've talked about so far. So for example, an adjacency matrix of a graph can be used to find the number of walks between any pair of vertices of a given length. So specifically, if we have an adjacency matrix A, then when we raise the matrix to the power k, each element ij of the matrix will give the number of unique walks of length k between vertices I and j. So if we go back to the adjacency matrix for the example graph we've been working with so far, we can see this matrix is just A raised to the first power. So in this case, k equals 1. So according to this statement here, this matrix should give the number of unique walks of length 1 between any pair of vertices. And we know that that's the case because each one just indicates that there's an edge between the pair of vertices, and that's a length 1 walk. But as we square the adjacency matrix, we can see that the numbers change. And so this matrix, each entry should encode the number of unique walks between the pair of vertices of length 2. So let's check it out. How many walks can we find between vertex 1 and itself of length 2? Now remember, a walk on a graph is just we follow edges to connect vertices for some length. And we're allowed to repeat vertices and edges. So if we start at 1, walk to 2, and then walk back to 1, that's a walk of length 2 that goes from vertex 1 to vertex 1, and that's the only one possible of length 2. So this is accurate. We can see if we look maybe at the entry of 2 and 3, that we should be able to find one walk of length 2 between vertex 2 and vertex 3. So if we start at vertex 2, we can go to vertex 4 and then 3 to find one walk of length 2 between the two vertices. And this pattern continues as we raise the matrix to a power. So this is raising the matrix to the power of 3. So you can see if you can count out the number of unique walks and how they match up with this matrix. And 4, 5, we can see that the number of walks really increases because we're allowed to repeat vertices and edges. But this is just a very simple way of getting this quite useful number. And if you're interested in a proof of this, I've linked it on the GitHub page, but it's also a great one to try figuring out yourself if you can. Matrix structure for storing graphs also have useful interpretations as they relate to a concept called the graph Laplacian. The graph Laplacian is a matrix that is another representation of a graph, and it can be used to easily solve a lot of graph theory problems. So it can be used to find the number of spanning trees of a graph, the number of components in a graph, and it can also be used to construct low-dimensional embeddings, which are really useful for a lot of really large graph theory problems where it's useful to project the problem into a lower dimensional space. So the graph Laplacian L can actually be defined in relation to the adjacency matrix that we were just talking about. We also need to consider this matrix D, which is just a diagonal matrix that has the degree of each vertex on the diagonal. So the graph Laplacian is just this degree matrix minus the adjacency matrix. And it can also be defined based on the incidence matrix that we were just talking about as well. So for the incidence matrix B, the graph Laplacian equals B transpose times B. So this is a theoretical link between the adjacency matrix and the incidence matrix, and it results in this matrix. Here I can show you the example for the graph that we've been considering so far that has many different properties, and I linked to a great explanation and starter if you want further reading on the graph Laplacian on the GitHub page. Now we're ready to start talking about some real graph datasets. So there are many datasets available currently for free online, and you can often download them as simple text files with one row for each edge and 2 columns indicating the 2 vertices that make up that edge. And for all the analysis we'll be talking about for the rest of the workshop, it's all implemented in Python, and I use the iGraph package. So you can pull up the GitHub page now if you're interested, and hopefully we'll have a few minutes at the end where you can test out loading in these graphs and calculating some of the computations yourself. So let's start looking at the datasets we'll be working with. The first is a Twitter dataset. This is showing a social network based on a single Twitter user where that single user isn't plotted, but all of the people they follow and who follow them are plotted, and there is an edge between 2 users if one of those users follows the other. So we can see, based on this plotted representation, that there's one really big cluster where many different people follow each other. Maybe this user follows like a specific community that's very closely knit. And then there are some others that have a few connections to the majority of the nodes, but are much more sparsely connected to the rest of the users. And then we see these two users on the edge that are only connected to each other. The next data set is a Facebook data set. So this is similar to the Twitter one, where each vertex represents a Facebook friend of one person. That one person isn't plotted, but there's an edge between two users if those two users are friends on Facebook. And so based on this representation, we can see that there seem to be a few different clusters, like maybe we can see 5 big kind of areas based on this representation that maybe represent different, maybe friends from high school, friends from college, friends from the workplace. And some of the vertices are more densely connected into that network than others. And then we also see these 3 vertices that are not connected to the rest and maybe represent random people that this user met, at one night while traveling or something like that. The third data set is called the Movielens data set. So in this graph, vertices are either movies or users that have rated movies. And an edge means that the given user, edges connect users to movies that they've watched. So I actually only plotted a subgraph of this graph because there are too many vertices to plot them all. But we can see that it looks kind of different from the Twitter and Facebook graphs. It seems like there are a lot of dots that aren't really connected to each other. And there are many more of these extra components that aren't connected to the main central component. And because of the structure of this graph, where there only can be edges between users and movies, this is what's called a bipartite graph. And we can color it in to make that more obvious. But in a bipartite graph, the vertices can be separated into 2 sets, and there are never edges between vertices in a given set. So here our 2 sets are users, which are in yellow, and movies, which are in green. So you can see that there are never any edges between yellow and yellow or green and green. There are just edges between users and movies. So we can see, for example, this user has seen many, many movies. Then our next data set is a mouse gene regulatory network. So this is a biological data set, and each vertex represents a different gene, and edges represent regulatory relationships between those genes. So this kind of network can give us a sense of how genes and gene expression are regulated in this specific mouse data set. So we can see there seems to be a large set of genes that are all co-regulating each other. And here again, I'm only plotting a subset of the vertices because the graph was too big to visualize all at once. But then we can see this little outreaching cluster of genes that seem to be regulating each other, but aren't as heavily connected to the rest of the regulatory relationships. Maybe this is like a separate regulation module. And then we have a few genes that kind of regulate each other, but don't have evidence of relationships with these majority of regulating genes. And then the final data set we'll be looking at is a graph of web connections between Stanford and Berkeley websites. And this data is from 2002. So vertices are websites either from Stanford, affiliated with Stanford or Berkeley, and edges are links between those web pages. So here I'm only plotting 1,000 vertices so that we can see what's going on. But this graph, again, looks kind of different than some of the other ones we've looked at. There seem to be a lot of vertices that then create these kind of clusters that maybe are interrelated with each other, but not really with the rest of the network. And maybe this could be like a PI or a professor, and all these vertices might be that professor's students that might interlock back to the professor and to each other. So now that we've gone over what these data sets are, you may think, okay, it's interesting to look at these data sets, and it seems like they might contain some interesting information. But other than kind of looking at graphs and making intuitive statements about what seems to be true, how can we actually move this analysis into something quantitative? Is there any way we could actually quantify some of these differences that we're seeing between these graph data sets? So that's what we're going to focus on next. Okay, now that we've defined our 5 example graphs, let's look at some of the graph attributes. So the first most basic statistic we can look at is the number of vertices in each graph. So we can see that both the Twitter and Facebook graphs have on the order of 100 vertices, whereas the Movielens and mouse data sets have an order of magnitude more, so they have tens of thousands of vertices. And then the Stanford Berkeley data set has an order of magnitude more, so hundreds of thousands of vertices. So that's one very basic difference between these graphs. And then the next most basic statistic we can look at is the number of edges. So if we fill that in, we can see that even though the number of vertices are kind of comparable between the Twitter and Facebook graphs, the Facebook graph has an order of magnitude more edges than the Twitter graph does. When we look at the Movielens and mouse data sets, we can see that the mouse data set actually has over 100 or around 100 times more edges than the Movielens data set, even though they have similar number of vertices. And the mouse data set even has more edges than the Stanford Berkeley data set. So we can see by comparing kind of the number of vertices and the number of edges, some of the characteristics and differences of these graphs. So for example, we would expect we can see for the mouse gene expression data set, there are more connections between different genes that regulate each other than between the different web pages that were analyzed in the Stanford and Berkeley data set. So another statistic we can look at is how the degree distributions differ between our graphs. So remember, the degree of a vertex is the number of other vertices it is adjacent to, so the number of edges coming out of a single vertex. So we can look at histograms for each of our data set of the distributions of degrees across all vertices in the data set. So for example, for the Twitter data set, when we're looking at the distribution of degrees, the minimum degree is just 1. So that means some Twitter users only follow one other person in the network, or only followed by one other person in the network. And the maximum is 158. So there is one user that either follows or is followed by 158 other people in the network. And we can see the degree distribution has its peak around, its median is at 82. We can see most of the vertices have around 50 to 125 connections within that network. So there are a lot of interconnections between the different users in the Twitter dataset. In the Facebook dataset, we actually see a kind of different pattern. We see more of the users, so more people are friends with 50 or fewer other friends in the network. So we see more of a loading towards the lower degree vertices, with one person in the network having 293 connections. So that person has many different friends among just this group of friends that's being analyzed currently, but that's outside of the norm, and we can see that based on looking at this distribution. If we look at the Movielens dataset next, we can see a pretty stark difference from the other two. There is one vertex that has a degree of over 10,000. That means either one user has seen over 10,000 movies, or one movie has been seen by over 10,000 users. But that is really out of the ordinary. The median number of degrees of a vertex is just 2. So that means that the vast, over half of the movies and users in our data set have been viewed by 2 or fewer users, and more than half of similar, about half of the users in our data set have viewed 2 or fewer movies. Looking at the mouse data set, we see a distribution kind of similar to the Facebook data set, where there is a weighting towards lower degrees, but it's not as extreme as the Movielens data set. So the median number of genes connected to other genes, so that means it is 273. So that's the median number of genes regulating other genes in this network. And then finally, looking at the Stanford and Berkeley data set, it looks most similar to the Movielens data set, where the vast majority of vertices, so the vast majority of web pages are connected to 7 or fewer, because it's the median, so half of the web pages are connected to 7 or fewer other web pages that are affiliated with either Stanford or Berkeley. But there is one web page that has just 84,000 connections to Stanford and Berkeley web pages, so it's kind of an outlier, and we can see that based on looking at these degree distributions. So next, one of the next simplest statistics to consider is the number of components of a graph. So if you remember from last time, a component of a graph is a subgraph within which every pair of vertices is connected by a path. So if we look back at our example graph, we can go from 1, let's choose a pair of vertices. We can choose 1 and 4. We can follow a path along these edges to get from 1 to 4. And we can see that we could do that for any of the vertices from 1 to 4. But if we want to find a path between 5 and 4, there's no way to do that because 5, there's no way of connecting it to these other vertices. And so in this case, we would have 2 different components. Sometimes they're called connected components in this graph. So when you're thinking of what a component is, it's just, or the number of components in a graph, it's just like the number of disjoint subgraphs that aren't connected by any edges. So in these data sets, both Twitter and Facebook only have 2 components. And then the Movielens mouse and the Stanford Berkeley data set all have many more. So 63, 97, and 676. So that means that there are many more disjoint subgraphs for these 3 data sets. And now when we look at these numbers, we can see the number of components, and then we can also see the number of vertices. And we can think, well, like, it's pretty different, right? If we have one component that has almost all the vertices, and then a second component that just has like 2 or 3, as opposed to all of our vertices being kind of divided in half between the 2 components. So the relative sizes of these components are interesting to know, especially maybe for some of these bigger graphs. We want to know whether, there are hundreds of pretty equally sized components or not. So if we want to look at and get that information, it can be useful to, again, look at histograms to show us these statistics. So we want to find histograms of the number of vertices in each component of our various example data sets. So for the Twitter data set, remember there were only 2 components, and here we can see that one of the components has a very small size. If you remember from looking at the images, the size was only 2, and then the one main component has around 170 vertices in it. This is similar for Facebook. Again, we saw that when we were looking at the visualization earlier, but there's one component that is very small, just 2 or 3 vertices, and then the second component contains everything else. And so looking at the Movielens data set, we actually see a kind of similar trend. There is one component that has over 25,000 vertices in it. So you can think of that as the most dense mass, many interconnections between users and movies. And then we have the other 66 components that are all very small. So maybe just like a user saw one movie and that's all they put into the system. And when we look at both the mouse distribution and the Stanford Berkeley distribution, they follow kind of the same pattern as the Movielens distribution. So they also have one really big component. We can see the sizes. They contain almost all the vertices, 42,000 for mouse and 654,000 for the Stanford Berkeley dataset and the largest component. But then we have all the rest of the components that are very small. So kind of like sparse, almost at the edges, only a few vertices together. And so when we're looking at these numbers, we might think based on this, like, oh, we kind of only have to pay attention to the main component depending on our application. Whereas if we saw a kind of more uniform distribution or many components with relatively large sizes, we might want to do separate analyses for each of those components or somehow pay more attention to that data. It could also be interesting for us to analyze why these components are so small, or kind of what makes a small component depending on our research question. So another statistic that can be very useful to quantify some of our intuition is the density of a graph. So the density of a graph is just defined as the fraction of possible edges in the graph that are present. So the number of possible edges in a graph is just the number of vertices in the graph, choose 2, because an edge is just defined by choosing 2 different vertices from the vertex set. So the density of the graph is just defined by the number of edges divided by the number of vertices, choose 2. And we can simplify that to see that the formula is just 2 times the number of edges divided by the number of vertices times the number of vertices minus 1. So if we look back at our original example graph, we can see that there are 4 edges and the number of possible, and so if we plug into this formula, we can see there are 5 vertices. We get that the density of the graph is 0.4. So that means 40%, or 2 out of 5 of the possible edges present are actually there. Now if we look at the actual density scores for our different example graphs, we can see that the social media sites, so Twitter and Facebook, have the highest densities by far of all of our data sets. We can see that the density of the Twitter dataset is highest at around 40%, followed by Facebook at around 10%. So that means there are a lot of very dense interconnections, especially for the Twitter dataset. And when we compare that to the numbers for the Movielens, Mouse, and Stanford and Berkeley datasets, those numbers are really small. So only a very small number of the possible edges are actually included here. And so density can help us identify sparse graphs. And when a graph is sparse, meaning it has few edges, we expect certain properties of those graphs. And also they can often be stored more efficiently in sparse matrix forms than dense graphs. It's also useful to think about how the number of possible edges changes as the number of vertices increases. So here we can see that, there are just 600 more vertices in the Facebook graph than in the Twitter graph. But the Facebook graph has, many more, like 20,000 more edges than the Twitter graph. But despite that, the Twitter graph is much more dense than the Facebook graph. And that's because the number of possible edges, the number of vertices choose 2 function, just grows really fast. So, even like these 14 million edges are only achieving a density of about 1.5%. So really dense graphs for many applications and many of the data sets we see are not very common for large data sets. So another statistic that we can look at is the girth of a graph. And the girth is defined as the length of the shortest cycle in a graph. So if you remember, we talked about in a previous workshop, a cycle is basically just a path that starts and ends at the same vertex. So if we are starting at vertex 2 and that transverses at least one edge. So then we can go from 4 to 3 to 2, and that creates a cycle. And looking at this graph, that's the only cycle that we see. So the girth of this graph would be 3. And 3 is actually the smallest value that we can ever have for the girth of a graph, because the triangle that we see here is the smallest possible cycle. If we, for a smaller, we can't have a cycle of length 2 because we're only allowing one edge between each pair of vertices. So looking at the girths of these graphs, we see that they're all as small as possible except the Movielens dataset. So for each of these other datasets, we can find, for Twitter, 3 different users who all follow each other, Facebook, 3 different people who are all pairwise friends with each other, or 3 genes that all regulate each other, or 3 web pages that all link to each other. But for the Movielens dataset, this number is 4. And we actually could have guessed that before calculating it, based on the fact that the Movielens dataset is bipartite. So because um, each user is only ever going to be connected to a movie, and each movie is only going to be connected to users, there's no way to create a three-length cycle, and therefore the smallest possible cycle we could get in this bipartite graph is length 4, and that is what we get. And it's actually another way of defining bipartite graphs are graphs that don't contain any odd cycles. The last metric we'll consider today is assortativity. So the assortativity coefficient is defined as the Pearson correlation coefficient of degree between vertices that share an edge. So we can think about this for our example graph. We can keep track of each edge, and for each edge, we can find the degree of each vertex that contributes to that edge. So we can see that for the edge between vertex 1 and vertex 2, vertex 1 has degree of 1, and vertex 2 has degree of 3. So once we create this whole table, we have our 2 degree columns, and so the assortativity coefficient is just the Pearson correlation of these 2 columns. For this case, it's negative 0.87. So that indicates that these the degrees aren't correlated in this graph, are in fact anti-correlated. Vertices are more likely to be connected to other vertices with degrees different from their own. And so the assortativity coefficient can range from -1 to 1. And just for some intuition, assortative graphs have, many vertices that are connected to other vertices of the same degree. So here we can see kind of the intuition for what that might look like. Whereas disassortative graphs, so graphs with low assortativity, tend to have high degree vertices connected to very low degree vertices. So we can see it as a different shape, and we might recognize these shapes from our example plots of the graphs earlier. And another important point about assortativity is it doesn't need to be computed based on degree. Like maybe you have a graph, a Facebook graph, for example, and you have the information of the height of each person, of each user. Then you could calculate the assortativity coefficient based on height. So you could see whether people of similar height, people are more likely to be friends with people of similar heights from them. So this can also be adapted to whatever your problem is. So here we can fill in the assortativities for our example graphs. And what we can see here is that in the Facebook graph, the assortativity is by far the highest. It's 0.5. So that means that Facebook users tend to be friends with people with similar numbers of friends. So kind of popular people are more likely to be friends with other popular people, and people with fewer connections are likely to be friends with other people with fewer connections. And this has actually been, this trend has been observed in many social networking graphs. And then we can see that the Movielens datasets and the Berkeley datasets are both the most negative degree assortativities. So that means that vertices are kind of more likely to be connected to other vertices with very different degrees rather than the same. Now that we've gone through some of those examples and calculated various graph metrics for many of our different example graphs, I hope that you were able to get a sense of how to analyze real graph data once you get it. And if you're interested, the Jupyter notebooks on the GitHub are available for you to play around, calculate these statistics that we've done, load in these graphs that we've been looking at, and kind of play with them yourselves. So if you have any questions, please put them in the Zoom chat or email me. Thank you.